All right, good morning, everyone. So usual announcements, homework next week. The hands-on project, the due date is Monday for your video links. And then there is the end of term survey. The link is on Canvas. Do that by Wednesday of next week. Okay, the other thing I wanted to show you is that I updated the course website with some information about the final exam. So, for example, in this section, I've just listed all of the various sections from the textbook that we will cover. So we worked on chapters 5 through 13, but we didn't cover every section of every chapter. And so these are the sections that we did look at. Okay, and then let's see, there are practice final exams at the bottom of the webpage. And so those practice exams are useful, but there are some topics that we didn't cover this year that are included in those practice final exams. And so I've listed here in the 2013 practice final, the questions 2, 13B, and 16 you're not responsible for. And in the actual final from 2013, problem 14 is something that we didn't cover. So when you're working through those, just remember that there may be a small number of questions that are on topics that we didn't cover. And so they're listed here. And then also, I have posted the formula sheet that you'll get with the final exam. It's the same formula sheet that you used for quiz number 2, just with some extra things added based on the topics of magnetism that we have been covering since quiz 2 finished. And so here it is, and you can scroll through that whenever you like. And so here is where we ended for quiz number 2, would have been probably the parallel and series resistors. And then cross product and all this magnetic field stuff is the new topics that we're covering now. So for example, Ampere's law we did last time is right here. Okay, so that formula sheet will be provided with the final exam, so you don't have to bring anything except something to write with and a calculator. Graphing calculators are fine. Okay, good. So is there any questions about any of that stuff? All right, so then let's just recap what we talked about last time. Ampere's law said that this integral of B dot dl around a closed loop had to be equal to mu naught times I enclosed. And this is like the magnetic field version of Gauss's law for electric fields. And so it's often used to find the magnetic field of different types of distributions of current. We did one application, we did the solenoid, and in this case, remember, we want to choose an integration path that's going to make solving the integral as easy as possible. And that integral involves a dot product between the magnetic field B and the path dl that we're following around this loop that we have to make. So if we make the path parallel to magnetic fields, then the dot product is easy to evaluate. If we make the path perpendicular to the magnetic field, the integral vanishes. And then when b equals 0, I don't care what the path is. And so we chose this purple path. Part 1 is parallel to the magnetic field, so b dot dl just becomes b dl. 2 and 4 are either perpendicular to the magnetic field, so the dot product vanishes, or they're outside the solenoid where the magnetic field is 0. And then part 3 of the path is always in a magnetic field of 0, and so it makes no contribution to the integral. So with all of that, it was only part 1 of the path that contributed anything, and we were able to show that the magnetic field of the solenoid is mu naught times I times the number of turns in the solenoid divided by the length of the solenoid. So capital N divided by this little L. Usually, or it's often the case that people will write capital N divided by L, the number of terms divided by the length, as little n, which is the density of terms, the number of terms per unit length. But they're the same thing. So that's the magnetic field of a solenoid. What I want to do is I want to do one more example of an Ampere's law type problem. And so what I've drawn here is a red integration path or a red Amperian loop. And I've drawn a bunch of currents. There's 6 of them. And they're either going into the page or out of the page. So imagine that these currents are, sections of a long wire. And the 3 of the currents, I1, 4, and 5, are inside this loop. And then the other 3, 2, 3, and 6 are outside. And so the question is, what would the result of the integral B dot dl evaluate to for this configuration of currents and for this particular integration path? Okay, well, all we want to do is we want to apply, let's see, the integral of B dot dl must be equal to mu naught I enclosed. And so this is Ampere's law. If we tried to solve for this integral directly, like actually evaluate the integral, that would be really, really hard to do because the path is some complicated shape. And the magnetic field, due to these 6 different currents, would also be really complicated. So I don't want to do it that way. I want to take advantage of Ampere's law, and I want to use the right-hand side to see if I can figure out what this integral would have to be equal to. So the first question is, what would I enclosed be equal to? I enclosed is going to be equal to what? Well, do I2, 3, and 6 contribute to our problem? No. So only currents that actually pass through this loop are going to contribute. So only currents passing through the loop contribute. And so those currents are I1, I4, and I5. So I2, I3, and I6 make no contribution. Okay, so the only other thing we have to worry about is, okay, we've got 3 currents that pass through this loop, and they're going to make up I enclosed. But 2 of them are pointing out of the screen, and 1 of them is pointing into the screen. And so how do I figure out which one makes a positive contribution and which one makes a negative contribution? Okay, let's start by drawing the magnetic field that we would get from I1. Right, these are currents in a wire, for example, and we know that the magnetic fields loop around these wires. So I1 is pointing out of the screen. If I put my thumb out of the screen, my fingers curl around in a anti-clockwise or counterclockwise sense. So here I would expect the magnetic field due to I1 would be going by the right-hand rule in this counterclockwise direction. And so this is, say, part of the magnetic field B1 due to current I1. Now, if you look at the part of that magnetic field that's next to the path, is the magnetic field going parallel or anti-parallel to our integration direction? So for example, if we look at a point over here, the magnetic field is pointing in this direction and our integration path is going in this direction. So this would be like a DL and this would be like a B1 here. And when we have to evaluate the dot product between B and DL, it involves the cosine of the angle between the two. What's the angle between B1 and DL that I've drawn there? 180 degrees. Cosine 180 degrees is negative. And so I could pick other parts, right? Over here, the magnetic field would be kind of in this direction, and then our integration path in that region of space is going sort of downwards. Again, it's kind of anti-parallel. And so the current I1 is going to make a negative contribution to the integral. So since B1 tends to be anti-parallel to the integration direction, it makes a negative contribution to I enclosed, or equivalently, the integral of B dot DL. On the other hand, if I did the same sort of argument for, say, let's say I4 is going into the screen, I put my thumb into the screen, and it makes a magnetic field that moves around in the clockwise sense. And so its magnetic field is going in the clockwise sense. And so over here, I get a magnetic field that's kind of in this direction, and the integration path is in that same direction. Those two vectors are basically parallel. So when you evaluate the dot product, you'll get cosine of 0, which is +1. So on the other hand, what were those currents? I4 and I5. On the other hand, I4 and I5 make positive contributions. So our I enclosed would be I4 and I5 make positive contributions, and I1 makes a negative contribution. And so therefore, the integral of B dot DL would be equal to mu naught, a constant, times I4 plus I5 minus I1. Okay, so if we told you the values of those currents, that's what that integral would evaluate to. Yeah.
I may have drawn my diagram wrong, but isn't I5 going out of the screen?
Oh, sorry. Yeah, you're right. Okay, yeah, you're right. Thank you. So I should say I4 makes a positive contribution, and I should say I5, like I1, makes a negative contribution. Good, thank you very much. So then I need negative signs here. Yeah, you're absolutely right. Good. So I want to come back to this picture at the top, and instead of having to draw the magnetic field of every current, I want to give you a little trick that you can use to figure out whether or not a current contributes positive or negative to this Ampere's law calculation. So let me draw this. So we had I1 and I5 coming out of the screen. So we had something like this. We had a I1 and an I5, and then we had I4, something like this. And then there was an integration path that looked, I don't know, something like that anyways. Close enough. And we picked that direction. So we could make kind of a version of the right-hand rule to figure out whether we should have positive or negative contributions from these currents. And the way you do it is you take your right hand and you curl it in the direction of the integration path. In this case, I'm going to curl my fingers to be going in the clockwise sense. My thumb points into the screen, and so currents that go into the screen contribute positive to the Ampere's law integral. And of course, that means currents that point out make the opposite, negative contribution. Okay, so right-hand rule for Ampere's law is going to be curl fingers of right hand in the direction of integration. Currents that are in the direction of your thumb make a positive contribution. Okay, good. Does that make sense? Any questions? All right. So what I want to do with the rest of the class is I want to do sort of the last major topic that we're going to cover. So we'll spend the rest of today and then the 2 classes next week on this final topic. And it's, in my opinion, the most interesting one that we have. And what we're going to try to do is we're going to try to come up with a method for converting mechanical energy or motion into electrical energy. And the reason that this is interesting is because this is the basis of almost all of the power generation that we make use of to power our homes and businesses and cities and whatever else you want to power. And so it doesn't matter if you're burning coal or if you're using hydro dams or if you're using nuclear power generation. They all take advantage of this method of converting mechanical motion into electrical energy. And so this is going to be a starting point of that discussion. So to orient ourselves, we are in chapter 13, section 3 of OpenStax University Physics Volume 2. And what we're going to talk about is motional EMF, or equivalently induced voltages. EMF is a funny acronym. What it actually means is electromotive force. And it's not a great name because it's not actually a force, it's going to be a voltage that we're going to generate. But the electromotive part makes sense, right? We're going to use motion to make some kind of electrical, not a force, but a voltage. But anyways, that's the term we're stuck with. And the way to understand it, to begin with, is pretty simple, actually. What we're going to do is we're going to make a uniform magnetic field. And so what I'll do is I'll make my magnetic field blue, and we'll say that it's uniform. And I'm going to make my magnetic field go into the screen. So we'll just draw these magnetic field lines going into the screen, like so. Okay, and then we're going to take a conducting bar, and we're going to place it in this magnetic field. So this could be a bar of copper, for example. So conducting bar. And all we're going to do is, what I said is we're going to try to convert mechanical motion into an electrical voltage. So we need to move the bar. And what we're going to do is we're going to pull the bar perpendicular to this magnetic field. Okay, so that's the idea. So we'll pull a conducting bar perpendicularly through a uniform magnetic field with speed v. Okay, well, what do we know about conductors? Conductors have a bunch of electrons in them that are free to move around. So these are the electrons that establish currents in circuits and things like that. And so what I want to imagine is that we've got an electron in here. And so there it is. And because it's inside the bar and the bar is moving, this electron is moving through our magnetic field. And we know that charges that move through a magnetic field experience a magnetic force. And so there's going to be a magnetic force on this electron. And in fact, not just this electron, but all of the electrons that are free to move around in this copper bar. Okay, so the mobile electrons in the conductor also move to the right with speed v. Therefore, they experience a magnetic force. So let's remember the magnetic force on a charge moving in a magnetic field is QV cross E. Okay, so let's first work out the direction of the force on this electron. So it's V cross E. So remember, for cross products, the right-hand rule was you put your arm in the direction of the first vector. In this case, it's the velocity. Velocity is to the right. And then I'm going to curl my fingers to be in the direction of the magnetic field. B is into the screen, so I point my fingers into the screen. And my thumb gives the direction of a force that a positive charge would feel. But we're talking about an electron, which is negative. And so if my thumb points up, a positive charge would experience a force upwards. Therefore, our electron experiences a downwards force. Okay, so we'll draw that force on our electron, and we'll say, okay, so there's going to be a magnetic force down. So we'll call this FB. Okay, the force on our electrons will be downwards. And the magnitude of the force is going to be Q V B cosine of the angle between the velocity and the magnetic field. The velocity was right, the magnetic field was into the screen, so they're perpendicular. And so, sorry, I got this wrong. Cosine is for dot products. We're doing a cross product. This would be sine of 90 degrees. And sine of 90 degrees is 1. And so therefore, our magnetic force has a magnitude of just QV times B, and it is downwards. Okay. All right, so let's imagine that we keep going. We keep pulling this thing to the right at a constant speed, and all of the electrons tend to drift towards the bottom. And so we'll end up with a pile of negative charge at the bottom of our rod. But if we take negative charge that was initially uniformly distributed and move some of those negative charges to the bottom, that's going to leave behind all of the positive ions, the atoms, the nuclei that are fixed in place. And so that's going to leave excess positive charge at the top of the rod. So as we move, as we keep pulling the rod, electrons pile up near the bottom and leave behind excess positive charge due to the atomic nuclei near the top of the rod. Okay, so let's draw that. We'll draw our uniform magnetic field. So there it is. And then let's imagine now we've been pulling this rod to the right for some time. So we'll have our velocity to the right. And what we're going to end up with is, what color did I make my electrons? Black. We're going to end up with all of these electrons kind of collecting at the bottom. And there's going to be a bunch of positive charge left behind near the top. Okay, and we're still pulling this thing to the right, so we still have an electron in here that has a magnetic force that's downwards. And so here's our magnetic force, FB, that's downwards. But now we have one thing more. If we have a bunch of positive charge at the top and negative charge at the bottom, what do we have between those two piles of charge? Like, imagine a capacitor. You have a positive plate and a negative plate. What do you get between them? Voltage difference, and a voltage difference is created by an electric field. So we're going to have an electric field that points from the positive charge to the negative charge. And so I've drawn this electric field outside, but this is the electric field that's inside our copper rod. So the separation of charge establishes an electric field E inside the rod. Okay, but these mobile electrons are charges and they also experience forces from electric fields. The force on a charge in an electric field is Q times E. This electron is negative, and so its force is in the opposite direction of the electric field. And so there's going to be an electric force that points upwards. So as more and more charge gets separated, the electric field gets stronger and stronger, and that electric force gets bigger and bigger. Eventually, what will happen is that electric force will exactly balance the magnetic force, and the charges will stop moving, and we'll have established an equilibrium. So the electric force on the electrons opposes the magnetic force. In equilibrium, the two forces balance, and charge stops migrating. Okay, so we'll end up with this equilibrium distribution of some negative charge at the bottom and some positive, excess positive charge at the top. Okay, so the equilibrium condition is that we know the condition, yeah. We know that the forces are in opposite directions. And so we just require their magnitudes to be equal. The electric force has a magnitude of Q times E. And we wrote down that the magnetic force has a magnitude of QV times B. And nice thing happens here, we could cancel the Q on both sides. And we end up with kind of a condition that's a little bit familiar. We have, therefore, that V is equal to E over B. Where have we seen that before? It was the velocity selector, right? We shot charges through an electric field of the capacitor with a magnetic field perpendicular. And so we have the exact same sort of thing happening here. I have, in this case, a magnetic field into the screen and an electric field that points down and a velocity that points to the right. So V, E, and B are all mutually perpendicular, just like they were for the velocity selector. And lo and behold, we get the same kind of condition that V is determined by the ratio of the electric to magnetic field. So this is similar to what we had for the velocity selector. Velocity selector. Okay, good. Another thing that we can do is we can rearrange to solve for E. So let's see, E is just going to be V times B. And this is a result that we're going to make use of. So I'm going to call that equation 1. All right. We said that we're going to try to make a voltage difference, and we haven't quite got there yet. At least we haven't calculated the value. We know that electric fields point from high potential to low potential. And so what we must have here at the top of our rod is a high potential. And here at the bottom, we have a low potential. And so what I want to do is I want to calculate the potential difference across that rod. And what we're going to need to do, or what we're going to need to know to do that, is the length of the rod. So I'm going to specify the length of the rod as L. Okay, so to calculate the voltage difference across the rod, we use, so we had a familiar result. We said voltage differences are this integral of E dot dl. Now what we're going to do is we're going to make some simplifying assumptions. We're going to assume that the electric field inside our rod is constant. And the dl is going to be the path from, say, the bottom to the top, or from the top to the bottom. We're just going to go along the direction of the rod, which is parallel to the electric field, and so the dot product is 0. So, sorry, the dot product is going to give a cosine 0 factor, which is just 1. So we're imagining that we have positive here, negative here. We have an electric field that points positive to negative, and we're going to integrate in a direction that's parallel to this electric field. So dl is parallel to E, and we assume that E is constant. And if we do that, the magnitude of the voltage difference is just going to be E times L. And then we sub in equation 1. So we sub 1 for E. And we end up with the voltage difference across our rod is VB is the electric field, and then times L. And this is the motional EMF. It's usually denoted as this curly E. But what I like to do is I like to really emphasize that this is just a difference in voltage. And just like a battery produces a voltage difference, the motional EMF is a source of voltage difference. Okay. If I pull the rod faster, I increase the speed, we get a larger voltage. The reason you get a larger voltage is because the magnetic force is proportional to V. So if I pull it faster, there's a stronger magnetic force. I need a stronger electric field to balance that stronger magnetic force. And so you get this bigger EMF. You could also make the magnetic field bigger, or you can make the length of your rod longer. All of those will contribute to a stronger voltage difference. So if this is a voltage difference, just like a battery, we should be able to use it to power circuits. So let's see how we could do that. And it's pretty simple. So we can use the voltage due to motional EMF to power circuits. Okay, so the picture is not going to change much, actually. We'll make our uniform magnetic field. That's going to be exactly the same. We'll have our conducting rod being pulled through the magnetic field. That's going to be exactly the same. So we'll pull this with some speed V. The only thing that we're going to add is we're going to add a little conducting track. And so my conducting track will have some rails. So we'll give it 2 rails. So these are conducting rails. And then we're going to connect the 2 rails together. I need to make a loop. If I want to have a circuit, I need a closed loop. So I'm going to connect the 2 rails together using a resistor. Okay, so the rod slides on a pair of conducting tracks that are joined on one end by a resistor R. Okay, so what we're going to end up with is, if I have an electron in my rod being pulled through this magnetic field, it's going to feel a magnetic force downwards, and so it's going to migrate down. But this time, because the rod is connected to a loop, it doesn't have to pile at the bottom. It will reach the bottom, and then it'll just continue circulating around this loop. And so our electron will move around the loop in this direction. And so we have this clockwise flow of electrons. Current is the flow of positive charge. So if I have electrons going in the clockwise direction, what I end up with is a current going in the anti-clockwise direction. So we have a current I going in this direction. So here's our current I. Okay, so electrons flow, what did we say? They go clockwise around our circuit, which corresponds to a counterclockwise current I. All right. So if we wanted to calculate the value of the current, so I is going to be equal to the voltage difference divided by the resistance, but the voltage difference we've already calculated, maybe we'll call this 2, is VB times L. And so this is VB times L over R. And so this is our induced current. Due to the motion of the rod through our magnetic field B. Okay, what I want to do is I want to show you a video of this actually happening. So on the course website, I have a link to a YouTube video that demonstrates this motional EMF, and I'm going to try to show that to you now. Let's see, I think I want to share the screen on the computer here. So let's do that. We'll share our browser. Okay, so here we are. And the link to the video is right here. Okay. Just want to make sure that I'm sharing this. Yeah, okay, good. So I'm going to click on the video. It's really short. It's like it's less than a minute long. So let me just show you what they have in this apparatus. This black kind of U-shaped thing, that is the strong magnet. And so it's making a magnetic field that points, I don't know, from top to bottom. Let's say there's a downwards a magnetic field. Then there's 2 bars in here. That's our conducting track. And then the demonstrator, whoever they are, is holding a conducting rod, and they're just going to slide that rod along this track. Okay, connected to the back here, you can't really see it, but there's 2 wires that go to this device. That device is a meter that's going to measure the current. And so what we're going to try to see is when the rod is being moved, do we detect a current? That's all that's going to happen. Okay, so here it goes. They did a bit of overproduction for some reason. I don't know why. But they will get to it shortly. So that little light on the current meter is at 0. And notice the current changes direction. Whether the rod goes forward, the current goes to the left. When the rod goes back, the current goes to the right. So the direction of the current depends on the direction of the motion of the rod. Okay, good. So that is the motional EMF demonstration. Let's see if I can get back to these notes here. Whoops. Sorry, I need to share screen, start. All right, here we go. Good. So we're back, and let's go to full screen. Okay, well, let's do a couple other things. We have 5 minutes left, and so I just want to get set up for what we'll do next. So the power dissipated by the resistor. So I said that we're going to try to convert mechanical motion into electrical energy. So let's actually calculate something that's related to energy. Okay, so who remembers how can we calculate the power dissipated by a resistor? Which one way to do it? I squared R, that's a perfectly fine way of doing it. So we just calculated I. So we know that this is going to be VBL over R is the current. And so we can call this equation 3. So this is from 3. So that's the current, and we have to square it, and then we have to multiply by R. And so what we end up with is just VBL squared. And then we have times R divided by R squared, and so we just get divided by R. So that's the power dissipated by our resistor. Let's call that equation 4. So it seems like we now have produced some energy that we've provided to our circuit. So that energy has to come from somewhere. And it comes from the work that we have to do to move the rod along these conducting rails. So let's go back and revisit our little setup here, where we had a conducting track. What color did I make my track? Purple. So we had a conducting track with a resistor, and then we had our rod, which we were sliding along this track. And we said that we were going to have a something like this. And then we had a magnetic field that was going into the screen. So that was our setup, right? And we were removing this rod with some speed or some velocity v to the right. Okay, good. So the other thing that we might have thought about is, well, hold on. Now we have a current in this rod, and that current is in a magnetic field. And I know that magnetic fields exert forces on currents. So let's just make a note of that. So now we have a current in our rod and currents in magnetic fields experience I can't spell today. Maybe I can't spell most days. Experience a force. Okay, if you remember, the magnetic force on a current was I L cross B. Okay, so remember the L is the length of the rod, and so we'll have the length of the rod that's in contact with the rails. The DL is the direction of the current. So I have a DL that's in the direction of the current here. Sorry, it's not a DL, it's just a DL we don't need, it's just a L. Let me fix this picture. So my L vector is in the same direction as the current. Now from the cross product, right-hand rule, L is up, cross with B is into the screen. My thumb points in the direction of the force, and that is to the left. And so by the right-hand rule, this force is to the left. And the magnitude of the force is ILB. L and B are perpendicular to one another, so the magnitude is going to involve a sine of 90 degrees, and the sine of 90 degrees is 1. And so we're going to get a magnetic force that's pointing to the left. Okay, that's where I'm going to stop. What we're going to do next time is we can see that if we pull this to the right, there's a force to the left. And so for us to keep pulling this to the right at a constant speed, we have to keep exerting a constant force. And therefore we're doing work. We're putting energy into that system. And we're going to calculate how much energy do we have to put in order to generate the power I squared R that we calculated in equation 4. Okay, good. Thanks very much. Have a good weekend. Yep.
I just had a quick question about practicing for the final. So
Yeah.
I'm going through the textbook.
Yeah.
But it doesn't have the answers. They don't really explain how they got to the answer.